Welcome all. The MfPH Next Generation Seminar Series is a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MfPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, épidémiologistes travaillants ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Philippsen Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, the Seneca, the Sogas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Philippsen opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, des Sosogas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Tanya Philippsen, a PhD student in applied mathematics at the University of Victoria, co-supervised by Yunlin Ma, Pauline van der Driesch, and Matthew Little. She holds a master's degree in public health from the University of Waterloo and a Bachelor of Science in Microbiology from the University of Victoria. Her research is focused on disease modeling, particularly for examining the impact of control measures and behaviors on disease transmission in populations. Notre invité aujourd'hui, c'est Tanya Philippsen, doctorante en mathématiques appliquées à l'Université de Victoria, co-encadrée par Yunlin Ma et professeur Pauline van den Driesch et Matthew Little. Elle est titulaire d'une maîtrise en santé publique de l'Université de Waterloo et d'un bachelor en sciences microbiologie de l'Université de Victoria. Ses recherches portent sur la modélisation des maladies infectieuses, notamment pour examiner l'impact des mesures de contrôle et de comportement sur la transmission des maladies au sein des populations. Her talk today will be a retrospective modeling analysis on the effects of control measures on SARS-CoV-2 transmission in Canada. Sa présentation aujourd'hui portera sur l'analyse de modélisation rétrospective sur les effets de mesures de contrôle sur la transmission de SARS-CoV-2 au Canada. Thank you very much for accepting our invitation, and the floor is yours.
Thank you very much. Thank you for inviting me to be here and to give this talk. I'm just going to turn off my video just to avoid any internet problems. So I will be here. So I'm going to be talking a bit about my research that I've been working on in the last couple of years, looking at the effects of control measures on SARS-CoV-2 transmission in Canada and taking a bit of a retrospective approach, looking at the first year of the pandemic in 2020. So here's just a brief outline of what I'm going to be talking about today. I'll just go over a bit of a background, some motivation for this work, particularly looking at homogeneous and heterogeneous populations, a little bit about wild-type SARS-CoV-2, and just some of the characteristics in terms of disease presentation and transmission. Some literature, some research results looking at the effectiveness of different control measures. This will go into some of my research objectives based on this motivation for this work. I'll go over a bit of the description of the multi-group model that I'm using, some parameter estimation and results of that process, and then we'll look at some alternative control measure scenarios, followed by some conclusions and next steps. So just a brief background, we all know and we've experienced with the the COVID-19 pandemic, when novel infectious pathogens enter a fully susceptible population, there are many health and economic and societal impacts, as we've seen and experienced over the past few years. Other novel infectious pathogens like SARS-1, Zika virus, Ebola virus, other things like that, there's a lot of uncertainty with these pathogens when they enter a susceptible population, particularly when there's very little known about the transmission of the diseases, who is at risk for severe outcomes, what are the different case definitions, who is a confirmed case, who's a probable case, what diagnostics are available, are there diagnostics available, is there treatment available, when should control measures be implemented and what type, and the list goes on. So there's a lot of evolving situations and knowledge that occurs that informs some of the decisions behind what occurs, but there's a lot of uncertainty in the first phase of an epidemic, and it's very difficult to assess the effects of interventions in these early stages. So, of course, there are many factors that are influencing the magnitude, the severity, and the duration of an epidemic. So, how many cases, what's the mortality rate, how long is an epidemic going to persist in a population? And these can be impacted by things like immunity, vaccination, fully susceptible populations, pre-existing immunity, transmission routes. Is it a vector-borne pathogen? Is it zoonotic? Is it human-to-human transmission? What types of social behaviors can influence how it's transmitted, what demographics are impacted, control measures, and so forth. So an initial introduction to some of this work that I've been doing is some of this motivation around population homogeneity and heterogeneity. So we're all probably very familiar with the SIR compartmental model, the susceptible, infectious, and recovered compartmental model. Here we have an SEIR model, so incorporating an exposed compartment. So we have our system of ordinary differential equations, where we're dividing up a randomly mixed homogeneous population into these disease-specific compartments, and they transition through these compartments based on disease characteristics. And so here we're assuming a homogeneous population. This is a very practical assumption. It allows for simplicity, just to reduce the complexity of the model. And so here are this little figure. So we have our homogeneous population. Everybody's identical except for the different epidemiological states that they have. So whether they're exposed or infectious or recovered or susceptible. And so when we include a homogeneous population or have the assumption of a homogeneous population with the model, again, it's very practical. However, it does ignore some characteristics and differences between subpopulations that may not be captured in this simple model. And so things like disease transmission probabilities, differential health outcomes, policy measure impacts. And so when we use the results of these models where there's a homogeneous assumption, some of these results can inform policies that may actually exacerbate health disparities in populations, in those that are most at risk for negative outcomes. And so in terms of population heterogeneity, we know that infection of susceptible individuals will be influenced by different heterogeneities and associated mixing behaviors. So here's another very realistic diagram of our heterogeneous community. We have different households, different sizes, ages, composition of individuals. Individuals in these households will mix with each other at different locations. They may be in different epidemiological states if they're infected or recovered or susceptible. And then they return home and mix at home with their family members or roommates. And so one of the benefits of incorporating this population heterogeneity in the models will allow us to have this finer biological and epidemiological realism in our results. and in the model construction. And this can help then to inform the development of more appropriate control measures when you're considering different populations, and also identify the risks of different health inequities and disproportionate burdens of disease. So now moving to SARS-CoV-2, the wild type or the ancestral strain. So the wild type strain that initially appeared and was transmitted in the first year of the pandemic appeared to result in very specific age-dependent outcomes, so infection, disease, and mortality. So in some of the literature, it was shown that it appeared that asymptomatic or mild SARS-CoV-2 infections were more in younger age groups compared to older age groups, and children also seem to have reduced susceptibility to the wild type SARS-CoV-2 pathogen compared to that of adults. And so during this time, many non-pharmaceutical interventions, as we know, were implemented to prevent transmission prior to vaccine availability and limited testing and diagnostics and treatment resources. So a lot of these NPIs were population-wide, general interventions, as well as age-specific interventions. So things like school closures, restaurant and bar closures, personal services, travel restrictions, working from home policies, things like that. And they were strengthened and relaxed over time, depending on the prevalence of cases in each region, resource availability, things like that. And so these different interventions, particularly the age-specific ones, can potentially lead to different impacts with respect to transmission probability and also contact mixing. And that's something that we want to look at. So looking at control measure effectiveness, particularly age-specific control measures, we're going to look particularly at school closures as a key age-specific control measures. And so in the literature, some studies have shown that school closures may not be effective when child and youth susceptibility or infectiousness is low, or when community transmission is high, or when responses to an outbreak are delayed. As well, it's been shown that decreasing contacts through community and school-based measures can reduce household risk when schools are open. And other studies found that in fall 2020, strengthening community and adult control measures in this time period were found to be more effective in reducing cases compared with that of school closures. So this is leading into our research objectives, and we wanted to take some of these results and findings and look at these particular questions. So how generic are these proposed conclusions or findings that strengthening interventions for adults might have similar or more or better effects compared to school closures in preventing transmission? So does it matter if there's regional differences in terms of control measure implementation? When these control measures are implemented, does it matter in terms of the time frame? What about the impacts of other control measures implemented at the same time? What if there are differences in susceptibility between populations? Can we then isolate the impacts of these age-specific control measures to evaluate their relative effectiveness on reducing transmission? So to answer these questions, we're going to take the approach of looking retrospectively at the SARS-CoV-2 pandemic in the period March 2020 to February 2021. We'll be looking at the impact of control measures on wild type transmission between and within two specific age groups in three Canadian regions. So we're going to be looking at 0 to 19 years, so children and youth, and then adults aged 20 years and older. So the time frame here that we're choosing is, again, primarily dominated by the wild type strain of SARS-CoV-2, and this is preceding widespread vaccination as well as widespread transmission of variants of concern. This is also March 2020 is when sustained community transmission was starting to occur more frequently following case importation. And then this is also when non-pharmaceutical interventions were being implemented and relaxed over time. So that's sort of the reason for this time period. So in doing this work, we also have to consider that there are a lot of uncertainties, again, with testing criteria and availability, capacity for case detection and things like that. So that's just something that we need to keep in mind in the background. So I'm using a multi-group model, an SEIR multi-group model. So these compartmental models, it allows to incorporate matrices that capture between and within group mixing. So we can then have more accurate disease dynamic behavior, and we can inform and evaluate group-specific disease control policy decisions. So here we have our SEIR model, but now we have two groups. So we have our K group, which is, again, our children and youth group, and our A group, which is our adult population. So some assumptions here to start with, we're not including any population dynamics in this model right now, births, deaths. We're not incorporating disease-related deaths, just given the time frame that we're looking at and the objective of this work. We also aren't including any asymptomatic or pre-symptomatic transmission or compartments, even though we know that they are a key part of transmission. The reason for that is that the data that we're using is primarily symptomatic cases due to the testing criteria, which typically require symptomatic presentation. And so we also wanted to keep the model as simple as possible to minimize the number of parameters that we need to estimate. But we do incorporate the E class, the exposed class, because there is a longer incubation period once somebody is infected, typically with SARS-CoV-2. So here, just a few parameters. We've got our delta parameter, which would be our rate of becoming infectious. And we have our gamma parameter, which would be the rate of recovery, where 1 over delta would be our mean latent period, and 1 over gamma would be our mean infectious period. The dashed arrows here in the middle will represent the contact rates between and within groups. So C sub kk would be between group contact rates between within the children and youth population, and similarly C sub AA would be within the adult population, and then C sub Ka and C sub AK would be within between adults and children and youth populations. And here we have also just a simplified parameter, alpha sub K and alpha sub A, and this will be representing the transmission rate. So taking the flowchart here, we now have our age-structured model, our system of ordinary differential equations. Again, the I subscript will be the children and youth, will represent the K or the A, the adults populations. On the right-hand side, our table of parameters. So we have some parameters that are known and some that are unknown. So the known parameters are the latent period, or the which would be our 1 over delta, our infectious period, 1 over gamma. These are going to be group independent parameters, and we've pulled that information from the literature. We also have a psi parameter, so psi sub k in particular here in the table, which represents the relative susceptibility to wild type SARS-CoV-2. This is for the child and youth population. In the literature, it appears that children and youth are about 50% as susceptible to this pathogen compared to that of adults. So psi sub k will be 0.5. As our contact matrix is also from the literature here. And we also do incorporate an importation rate for one particular region and one particular period, and this is pulled from the data. It's only going to be incorporating importation rate of adult specific cases based on what the data has shown. So we also do have some unknown parameters, and that would be our beta parameter, which is our transmission probability per contact. This will need to be estimated. And then we also have our epsilon K and epsilon A parameters, and these will be the transmission reduction by control measures. And this will fall within the range of 0 to 1, where 1 represents no control measures being implemented, business as usual. And then parameters between 0 and less than 1 represent some measure of control being implemented. And so we can see that the beta parameter, or transmission probability, is going to be modified by the susceptibility parameter, psi, and the control parameter, epsilon, as well as the contact rates. So that kind of incorporates some of the heterogeneous mixing happening here. So some key measures for our model. So we have our basic reproduction number, R naught, which will be the average number of secondary cases resulting from one infectious individual introduced into a fully susceptible population, where R naught is greater than 1, the disease will persist, and when it's less than 1, the disease will die out. We also want to look at the control reproduction number, R sub C. So this will be the average number of secondary cases in the susceptible population when control measures are applied. So this will be the case when epsilon A or epsilon K, or both epsilon A and K, are less than 1 and greater than or equal to 0. So using the next generation matrix method, we then can determine, we can find the spectral radius rho of this matrix here, which will be the magnitude of the dominant eigenvalue, and that will be R sub C. And so when all of the control parameters equal to 1, that means that there's no control measures in place, and our RC will reduce to the basic reproduction number. So we're going to be looking at 3 different geographic health regions. We're going to be looking at the Calgary Health Zone, the Greater Toronto Area, and the Greater Vancouver Area. So the Calgary Health Zone in 2020 up to 2021, February 8th, 2021, they reported 34% of the provincial population and 38% of the provincial confirmed cases up to this point. The Greater Toronto Area is consisting of 4 specific public health units. So I believe we have York, Durham, Peel, and Toronto. And so they report 46% of the provincial population, and they reported 68% of the provincial confirmed cases during this time. And the Greater Vancouver Area, which consists of Vancouver Coastal Health and Fraser Health Authority. And they report 62% of the provincial population and 82% of the provincial confirmed cases. So all of these regions are urban centers. There's a lot of commuting and between and cross-boundary mixing and residents and things like that. They're in small geographic areas. So that's sort of one of the reasons, some of the reasons why we chose these areas. These also have major international airports where the initial seeding of the pandemic initiated from other countries. So that's sort of what we're going to be looking at here. So we're looking at the data from these 3 regions. We've pulled the data from different sources. Here we have the cases in log linear scale. So just going over what you're seeing on the figure here. So the left-hand column is going to represent the Calgary Health Zone. The middle column will be the Greater Toronto Area, and the right-hand side will be Greater Vancouver. So the log linear plots here of cases in children and youth will be the blue dots, and the adults will be the red dots. And so we're just looking at them across the 3 regions. So this top row here, because there is a very small proportion of cases in children and youth during the early phases of the pandemic, it's really hard to kind of look at the concurrent trajectory within each population. So here we can now kind of see the concurrent growth and reduction of cases in each age group in this format. So the curves are roughly parallel in this plot. The disease dynamics in adults and children are very closely coupled, and there are similar exponential growth rates, typically between children and youth and adults. And you can see that later on in the period in particular. There are a few differences, particularly in the early stages of the pandemic in the Greater Toronto Area and Greater Vancouver, so those 2 boxes there. And this is potentially due to cases in long-term care homes in early 2020, but we'll get back into that in a minute. I'll talk about that a little bit more. So now we're going to take the adult cases and the children and youth cases and split them up. And we're going to look at the control measures that are associated with each population. So here in the second row, we have our adult population or adult cases over time. The colored background here, the ribbon in the background reflects the periods where non-pharmaceutical interventions were implemented, strengthened, relaxed over time. These are typically community-wide as well as adult-specific control measures. So this is just kind of representing the changes over time. And so note that the colors here don't represent the same control measures in each region. They just reflect the relaxation and the strengthening that are occurring according to what had been implemented in the previous period. So you can kind of see where the relaxation is occurring and the strengthening is occurring, like in the summertime and in the winter. The third row here is our children and youth population cases. So the colored ribbon here is going to be reflecting school-related measures. So here we have red will be our school closures, blue will be summer holidays and winter holidays, green will be school reopening with precautions in the fall of 2020, and yellow will be any sort of hybrid measures where there's both in-person and at-home learning. And the dashed line will be the September 2020 initial school year, 2020 fall school year start. And we'll just bring the dashed line up so we can compare. So what we can see here is that there's generally some exponential change at each major control period change. And so this also does depend on the type of control measure being implemented in each region. So that's not really reflected here, just the strengthening and the relaxation actions being taken. So this coloring really helps us to segment the time frame in question based on what's being implemented and relaxed. So you can see in the summertime, like I guess I don't know if you can see my arrow, but the summertime, there's definitely some growth and relaxation happening when schools are open in each region. There's growth happening in the children and youth cases. And so this is a good way to kind of see, kind of align the cases as well as what's occurring in terms of strength of control measures in each location. So as I mentioned earlier, there are a few parameters that we don't know. So we need to estimate those parameters. So we're going to do this in a couple of different steps. So our first step will be to estimate the baseline transmission probability beta. So this will be during the period where there are no control measures being implemented. So business as usual. We're using maximum likelihood estimation, Poisson regression. Here we're going to be fixing all of our parameters, our delta, gamma, our susceptibility parameters. Our epsilon parameters are going to be set to 1 just to represent no control measures. And then in the Calgary region, we're also incorporating an importation parameter just because of the data that we're using. The Greater Toronto area data and the Greater Vancouver area data that we're using, we're able to distinguish local cases from travel-related cases, but the Calgary data set doesn't allow for that. So that's sort of why we're incorporating this importation parameter. So we use a very narrow time frame, just given the data that we have and sort of what's happening before major control measures are implemented, occurring in mid-March. So the period that we're looking at is between, let's say, 10 and 16 days or so. So the parameters for the transmission probability are just there on the right-hand side of the table. So once we have our transmission probability parameters for each region, we then want to start estimating the epsilon K and epsilon A parameters, so our intervention strength for each subsequent period for the rest of the time frame that we're looking at. So here we're going to be, again, fixing the parameters delta, gamma, psi, and we're not using importation parameter anymore for Calgary, so it'll just be every region will be the same in terms of the parameters used, and then the baseline transmission probability is also going to be fixed now for each region going forward for each subsequent period. And so we're going to be estimating these control parameters in each period, and the end state of the S, E, and I output from each period is going to be the initial condition for the next period as we go through this fitting process. And to add more precision to this, we're also going to be incorporating or considering the latent period of about 6 days. And so the end state is actually going to be 6 days prior to that. And that will be the initial condition for the next period. Here we go. So here is just a quick overview of the fitting process. The results of the parameter estimation, our fitted curve, and the associated control measures. So we'll go through each section one by one. So here in the top 2 rows, this is going to be looking at the adult population in particular. So again, we have Calgary on the left-hand side, Greater Toronto in the middle, and Greater Vancouver on the right-hand side. The top row is representing the time-dependent changes in the estimated epsilon A parameter. So this is the parameter that is capturing the reduction in transmission probability when interventions are applied. When epsilon is 1, there's no control, and when it's 0, there's very strong control measures occurring. And the second row is going to be the fitted curve to the cases in the adult population based on the parameters here. And again, the colored ribbon in the background is going to be the sequential control measure periods in each province when they're implemented and strengthened. And the dotted line again is the fall 2020 school opening period. So the next 2 rows is now looking at the child and youth population. So the third row is going to be, again, the time-dependent changes in the epsilon K, the estimates for epsilon K. Again, 1 is going to be no control, and 0 will be very strong control measures. And the fourth row will be the fitted curve based on these parameters to the cases in children and youth. And the colored ribbon in the background here is going to be reflecting the school calendar interventions during this period. So the curves fit relatively well to the adult data, so in the second row in all 3 regions. However, in the child and youth population, we see that there's actually an overprediction of children and youth cases in the Greater Toronto area. This is also seen in the Calgary and Greater Vancouver regions, but it's not as obvious given the scale here. So we were kind of looking into this and trying to figure out why this could be happening. So some of the reasons could be that the testing criteria was very restricted during this time. This is early on in the pandemic phases. There were testing backlogs reported around this time as well. And we also, in looking further into this, there were actually a lot of long-term care outbreaks in the Greater Toronto area, which there was a lot of increased testing in these particular locations. And so what could be happening here is that the model, based on the structure of the model and the contact mixing between populations and age groups, there may be an expectation of more child and youth cases than are actually reported due to an assumption that there's more interaction occurring between individuals that are infected who may be living in long-term care homes and youth and children. But this may not really be reflective of reality. There's lots of restrictions in place, and mixing is not going to be, may not be the same as would be reflected in the contact rates that we have in the model. And so this is one of the things that we were considering as being a reason for this overprediction. So we did do a test to remove all the long-term care associated outbreak cases from our adult population. There was still an overprediction when we ran the model again, but it was reduced by about 50%, which means that there's likely other factors as well occurring here, like the testing criteria, maybe things like mild symptoms in children and youth, other things like that. And so, yeah, so I just wanted to point that one out there. So some notable results here, which kind of are very reflective of the contacts between and within age groups when control measures are applied. So Again, epsilon is going to be reflecting the reduction in transmission based on control measures. So the first half of the time frame here, it's not overly obvious based on the case data. There's some growth, but it's a small scale. The control parameter estimate figures, the first and the third rows, allow us to zoom into what's happening there. So we can see that when control measures relax, when they're community-wide and age-specific, so hybrid school, summer holidays, relaxed mixing in the community, things like that, this is actually reflected by the increase in the epsilon estimates. So that's reflecting relaxation and or not as strong measures. And this is particularly shown in the children and youth population. And this is in all three regions, so where those arrows are. After September 2020, when school begins, we can see again that strengthening of control measures is reflected in the estimates in the adult group. So there was a lot of strengthening occurring around this time in different capacities in each region. But the control parameter estimates have a reduction over time, as you can see. And this is shown somewhat in the children and youth population estimates, so in the third row there. But due to the addition of in-person mixing when schools are open within group mixing, this is adding a layer of complexity in this estimate, the trend of the estimates in terms of where they're going. So here we've been able to consider these two populations given different susceptibility, different behaviors and control measures at times. And so we were able to isolate the impact of these control measures in each population. And we can also see that the effects of age-specific control measures can also impact other populations. So for example, on the left-hand side, where the two ovals are, so Calgary winter holidays, when schools are closed for the winter break, we can see that there is an increase in estimates in both population groups, which could reflect increased mixing between and within both age groups. So potentially more transmission occurring, but also more mixing occurring just based on activities happening within families and between households. In the Greater Toronto Area at the start of the fall 2020 school year, in the middle column there, there's a clear relaxation of control measures in the children and youth population in the third row, and a strengthening in the adult population in the top row. This could be due to strengthening of control measures in adults. It could be reflective of a change in the contacts when schools are open, so more interactions between children, and then less interactions between children and adults. So interactions between adults then could be increased or reduced depending on control measures occurring. Here it shows that there is a reduction happening. And then in Vancouver, also shows a relaxation in both populations in fall 2020. So the estimates increase, which reflect a relaxation. At winter break, we can see that the child and youth control measures do strengthen while adult control measures relax. And this could also be due to the changing interaction of adults and children during this time. And so one thing to note, of course, the selection of timeframes here may be impacting some of these estimates. So I tried to get them as true to what was happening based on the data and the intervention data that I was able to capture from the Canadian Institute for Health Information from their COVID-19 intervention database, as well as other details from news reports, press releases, things like that. So some of these timeframes could be impacting some of the estimates, or there could be other factors not accounted for. But this is a pretty interesting result, I think, which shows kind of the differences in control measure impacts. So now that we have our estimated parameters for control measures for this period, this time frame, and all of these sequential periods, we wanted to consider some alternative scenarios. First, for the fall 2020 peak. So here in black, we have our original model fit. The gray dots are reported cases. The top row are the adult population, and the bottom row is the children and youth population. And again, we have Calgary, Greater Toronto Area, and Greater Vancouver from left to right. So what we're doing now is we're going to be varying some of these control parameters. First, we're going to do this one at a time. So the dark blue curve is reflecting the scenario where we are strengthening control measures in the children and youth population. So essentially, we're going to be considering school closures in fall 2020, and we're fixing all of the other estimates as is. And so when we run the model here, we can see that there's actually not a very significant impact when considering the original fitted black curve in both populations. There's not much of a reduction when we consider a very strong control intervention like school closures. So it's just a bit of a reduction, but not too much. Then we want to look at varying adult control measures only. So the dark red curve is reflecting just a moderate enhancement of adult control measures. So we're strengthening by 20%. So we can see that there's quite a significant impact on case reduction compared to the dark blue curve, which really shows how impactful or effective adult-specific control measures can be in reducing transmission in both populations. Then we want to look at varying two parameters. So the light blue curve, we're going to be considering the scenario where schools are closed, and we're also strengthening adult control measures by 20%. And the result is that we can see that there is a small reduction beyond the dark red curve, but not significantly. So again, the dark red curve is where we're just varying adult-specific control measures. And so this really shows that the addition of school closures on top of that really doesn't make a significant difference when compared to just strengthening adult control measures. And then finally, the pink curve will be just moderately strengthening both adults and children and youth control measures by 20%. This is very similar in results to that of the dark red curve. And here again, it's showing that adult strengthening has the most impact on reducing transmission, reducing cases. So our next scenario then is to consider the joint case where schools are open in the spring and in the fall at various precautionary levels, and additional adult control measures are implemented. So here again, we have our black curve, which is our original model fit. Our gray dots are going to be the reported cases. The dark green curve now is the scenario where schools are going to be open in the spring with no additional precautions, so business as usual. And the fall scenario remains as it was in fall 2020. So no changes to the parameters there. So what we can see here is that the dark green curve, there's quite a large increase in the Calgary Health Zone in the fall 2020 period. There's also increases in Greater Toronto and Greater Vancouver. In comparison, the dark red curve, schools are open in the spring. Here, this is the case where there's precautions in place in schools, so similar to what occurred in fall 2020. The fall parameters remain the same. Here, the precautions implemented in the springtime reduce the amount of cases in all regions, but they still result in more cases than what originally occurred when schools were closed in the springtime. And this is in all regions. The light green curve is now considering schools open in the spring, business as usual. And here we're adding an additional adult control measure, strengthening in the fall of 2020. Everything else is remaining the same. There's the greatest impact in the Greater Toronto area. So it's reducing the number of cases below the fitted curve in both adults and in children and youth population. And so it's quite effective when adding the moderate strengthening of adult control measures here. There is a reduction in Calgary and Greater Vancouver, but would still, in this case, produce as many or more cases in both populations. And then finally, the light pink curve here considers schools being open in the spring with precautions, such as what were implemented in the fall. Things like cohorting, I may have not mentioned that before, or things like that, and strengthening adult control measures in the fall by 20%. This is the most effective approach in all regions. So the impact of additional adult control measure strengthening is really obvious here in all of the regions. Just briefly, to not go too long into this one here, we can also consider things like other pathogens. So where populations have equal susceptibility, such as with influenza, perhaps, or other transmissible pathogens. So here we can consider the fall 2020 peak, and we're going to be assuming that susceptibility is equivalent. So that would be the black curve, where all the other parameters are kept as is. There's a lot of variation across provinces. Definitely a lot of increase in cases in the fall 2020 period. The greater Toronto area and Calgary, when we look at the dark blue curve, so this will be the school closure curve in the fall, is less effective than strengthening adult measures in those regions, so the dark red curve. And in Vancouver, the dark blue curve appears to be more effective in the children and youth population compared with adult strengthening in the red curve, which is kind of interesting and need to look into this a little bit more. In the adult population in Greater Vancouver area, strengthening the adult measures, the dark red curve has approximately an equivalent effect to school closures, which is kind of interesting. So here it seems as though the most reasonable scenario in this case is the pink curve, where measures in both children and adults are enhanced equally. Of course, when we say effective measures, this is also depending on severity of the disease, population at risk, other factors, what risks and benefits there are when implementing particular interventions. So some concluding remarks and some findings here. So we see that a slight increase in adult-specific control measures really does have a similar and even greater effect on reducing transmission in both populations when compared with drastic strengthening of control measures like school closures in children and youth in fall 2020. And this is consistent across all regions, despite the differences in the types of control measures applied at the same time. Closures in schools in spring 2020 has a larger effect in Calgary. This could be due to relaxed adult interventions during this time. So if you remember seeing that really large green curve, so having schools closed during that time compared to having them open was really quite effective there. We also saw that there were some overprediction of cases with this model, particularly in children and youth during the early stages of the pandemic. So this could be a result of testing capacity, testing rates, lower testing rates in children and youth, priorities, testing backlogs, things like that. So it could be resulting in underdetection of infections in this age group compared to an older population. As well as the potential contribution of long-term care home cases and possibly acute care as well. Some of the data, the case data are from individuals in acute care. And so that is also, could also be contributing to this over prediction here. So some next steps is to incorporate more data to refine some of the parameters, particularly with symptom onset and testing dates. So the delay between symptom onset and testing, and with the assumption of subsequent self-isolation. So that would change our gamma parameter, removing individuals from the potential of transmitting the population sooner than what we have in our model. We also want to consider more heterogeneity in population mixing, such as refining the age groups, considering imported cases, outbreaks in acute care and long-term care homes. As well, the contact matrix may change with control measures. So one thing we want to consider is maybe remove the contact matrix, but consider spatial patches instead to represent location-specific mixing. And that's something that we're working on as well right now. So yeah, I just want to acknowledge the support for this research, as well as my supervisors. Yeah, so thank you for listening to this talk, and I'd be happy to take any questions that you might have.
Thank you very much. So